Greetings, fluid mechanics enthusiasts. Here is Leonardo, and on this video I would like to talk about some particular equation which have some interesting properties very useful for solving fluid mechanics problems, which is the Poisson equation. So first of all, I'd like to talk about an issue regarding navier-stokes equations for incompressible and of course Newtonian fluid. So if you may recall, here we have the continuity equation, which is a conservation equation for mass and here of course is the navier-stokes equation, right? Which is conservation of momentum. Well, as you can see here, we have a set of 4 equations for 4 variables, which are the 3 components of velocity, which is usually denoted as u, v, and w, and p, which stands for the pressure. However, we have, if you take already a good look at these equations, you notice that we have an issue here regarding the pressure. So when you're doing the integration of navier-stokes, it could be a numerical integration, or you're solving them in analytical, you're searching for an analytical solution of the navier-stokes equations. Usually what you do is, what is done is you separate this term here from the rest. So we have here is the convective acceleration, the pressure term, and the forces due to viscosity, the diffusion of viscosity. So now you can time integrate this equation here. Okay, so we do a partial integration and you have the components u, v, and w in the next time step, right? However, how do we obtain the pressure? As you can see, we have no equation, an explicit equation for the pressure. We only have remaining the continuity equation, but pressure doesn't appear explicitly in these equations. So how can we get around that? This is a major problem in solving fluid mechanics problems. Does not appear explicitly in these equations. what we have to do is look for a Poisson equation, which we can then integrate the pressure in terms of the sum of the known as priori velocities. Okay, so what we're gonna do is for didactic purposes and for aim at doing it in a simple way, I'm going to derive the Poisson equation for a two-dimensional Navier-Stokes in a Cartesian frame of reference, but you can extend, after we'll see that, you can extend this equation to higher dimensions and other systems of coordinates. So as usually we begin with Navier-Stokes. Separating the x direction and the y direction. So here's the gradient of pressure plus this diffusion term. So here is your first term, x direction, and for the y direction we have equals, here is the density, ρ, dp dy plus the kinematic viscosity, dv dx, second derivative, partial derivative. Okay, so here on y direction. Now what we're gonna do is, and of course we have the continuity equation which we will use in a later time. Let me write it down here, the continuity equation. Okay, so what we're gonna do now is take the partial derivative of the first equation, which is this one here, with respect to x, and see what happens. Okay, so taking this equation and deriving respect to x will think as follows: plus u square. Remember here on this term you have to apply the the product rule, right? So his term here will appear squared plus dv dx du dy plus v equals to minus and getting short here plus so there you go. And for the y direction we'll derivate this equation, we apply the derivative with respect to y. So we obtain the following. du dy dv dx plus u dv dx dy plus dv dy. Here will be squared plus v okay. So this will be equal to second derivative of p with respect to y plus, and here the diffusion term, plus okay. So the next step now will be to sum these two equations here and see what we can get. So this one plus this one here, we will sum these two equations. And we get the following. Will be the time derivative of ux plus, sorry, here is v plus du dx squared plus dv dy squared, these two terms here, plus here we have these terms repeated, it's 2 dv dx du dy. Okay, so this will be equal to, wait, let me check here and here. Ah yes, here we have plus u, which multiplies du dx squared plus v dv dy squared plus this will be the equation for the right hand side. Okay, we'll do the left hand side later. So what we have is this term here is 0 because of the continuity equation. This will be equal to the continuity equation, and these two terms here, we can work with them as follows. Here we have d dx du dx plus dv dy. which is also 0 due to the continuity equation. And here we have d dy du dx plus dv dy, which is also 0. So these two terms here vanishes. Okay, so on the left hand side what we are left is these terms here. Okay, so let's do the left hand side. On the left hand side what we are left is this. Sorry, the right hand side. We'll get minus whole dx plus dp dy plus kinematic viscosity Okay, so in a similar fashion as we did for the convective term, to eliminate this term, we're going to eliminate this term using of course the continuity equation. So here we have second derivative of du dx plus dv dy, and the second derivative with respect to y of du dx plus dv dy. Okay, so this is this term here. Of course this is equal to 0 because of the continuity equation, so all these terms here are 0. And on the left hand side, sorry, the right hand side, what we are left is the inverse of the density, dp dx dp dy, second derivative of p. So putting all together, we arrive at the following. Here we have du dx squared plus 2 plus dv dy squared, which will be equal to minus inverse of the density, dp dx plus dp y squared. As you can see now, we arrive at the Poisson equation for 2D, two-dimensional flow in Cartesian coordinates. So we can express this term here as f, and here it is equal to minus the Laplacian of p divided by O. Okay, so the Poisson equation will be equal to minus 1 the Laplacian of p divided by the density equal to this term here, which corresponds to this, the derivative of u with respect to x squared plus 2 times du dy dv dx plus dv dy squared and equal to the Laplacian of the pressure. So we finally obtain an equation for pressure. From this equation here we can isolate the pressure using integrations, partial integration, or analytically or numerically integration of this equation, and obtain P knowing the previous values of U and V. Okay, so thanks for watching, hope you enjoyed. Don't forget to like and subscribe and share this video with others. See you next time.